Alright, hi everyone. Welcome to my channel to take the lectures. So in this video, we'll complete the rest parts of the past questions. Okay? So now we've talked about a lot from the previous one, completing, doing a lot of topics that covers the past question. So we've done all this. Now something we did say in the last video, when we talked about diversity factor, is this. What we have down here. Okay, allowance for diversity. So the thing is this, like we said in the last one, that for the diversity factor, being that we are not going to make use of all the total, we are not going to make use of the total load at all times. Okay, at home we will use some part of the load. Okay, some part of the installed load, we use some parts. That's your TV may be on, and then just maybe two bulbs or one bulb and then one fan. Then your cooker is turned off and some other things. So the load you use, maximum load, that's maximum actual load, you make use of divided by the total load. That's your diversity factor, total installed load. So this is not the case for every home. Okay, when I say this is not the case, I mean some homes or some places you have your diversity factor can be let's say 0.8, while in some other places your diversity factor can be 0.9, some can be maybe let's say 0.5 or less. Okay, so the thing is that the amount of load being used in one home differs from another home. Now, but domestic usage is kind of similar, but for industry, for factories, for hotels, it's kind of different. So that means the diversity factor for individual household, okay, is different from the diversity factor for small shops, and it's different for hotels. Have we seen it now? So that's why we have couples or final circuit feed from conductors or switchgears to which diversity factor applies. So for lighting, in where type of premise for homes, lighting for homes, this is the use 66% of the total current demand. Okay, that's for lighting. Then for heating, of course, 100%. Okay, so this table is something I think we should not even memorize, but it's there. But if you want to memorize it, fine, but it's there. This table is there. You can also check online for it. Okay, and it's in yeah, not this one from the textbook, from our handout. Okay, so you can check this online. So if you want to, okay, what's the diversity factor for hotels in terms of heating? Of course, I should get full load, 100% of the full load. Okay, so hotels or small hotels, and for what? Heating and power, all these heater and things like that. Okay, now that you say 100% of the full load. Now, if you don't really understand what all this means, that's not an issue. Okay, just know that there is allowance for diversity, and there's a table for it where you can just make reference to if you want to consider the diversity factor for individual household, for small shop, and for small hotels. There's something I've observed in this course design and installation, is that there are a lot of tables, there are a lot of set values. Okay, so just bear that in mind. Now, the next thing we are going to quickly talk about, still from the past question, is this motor installation requirement and operation. We are asked to state the requirement for motor installation. Okay, what do you need to consider? What do you need to consider? And then the operation from starting to running, protection, and then stopping or isolating. Okay, so this is just a summary. What I did here is a summary. So you can, of course, browse for that, study for that, but this will just give you an idea of how it looks like. Okay, so for motor installation, the things we need: cable sizing. I want to say cable sizing, you see, is to prevent overheating and voltage drop. If you use the correct cable size, of course, overheating is prevented. But if the cable size you make it up is too small, You know, they gave an example in the last video saying that it's just like a pipe. So the water flowing through this pipe, okay, will be less compared to the water flowing through this pipe. It's a larger pipe. I'm saying it now. Larger pipe, smaller pipe. So consider the pipe as wire size, cable size. So for a larger cable size, it will allow larger amounts of current to flow through with less heat. But that same amount of current flowing through this one, you want to force that same amount of current to flow through a smaller size, it will produce heat. Okay? To produce heat. So yeah. Yes. So you have to consider the cable size and the amount of cable size. Okay, and what the rating as current and then voltage. Consider cable size. Okay? So then protective device, shield motor from overload or fault. You need to make use of a protective device, all this miniature circuit breaker, switches, gears, okay, to shield the motor like if there's an overload or fault, it will just strip off instead of damaging the motor. So you have to protection devices. And then starter type. Now, this starter type is to control inrush current. Okay, inrush and save start to control inrush and save start. The idea of inrush current is that current acts just like when you open a valve. You know there is this rush of water through the valve at once. That first rush, okay, is what considered as the inrush current. Okay, so you also consider stable type. Then isolator and then switch gear to allow for safe disconnection and then maintenance. Okay, we've already talked about switch gear. And then earthing is to prevent shock. That's another requirement. That you earth the motor. And earthing is just connecting the metallic parts of a device or an appliance, connecting the metallic parts, okay, which is not expected to carry current, connect the metallic parts to ground. Okay, I think we talked about earthing. Yeah, we did. Okay, we will. So we'll get there. And then location and ventilation. You select a place where you can have your motor and there should be ventilation, airflow. Okay, to improve motor life and performance. So that is for the requirement. Note what I just said. All I just said is a summary. This is summary. Okay, you can go and expand on this. But this is summary, just the idea of it, what you need. Then one thing to do, I didn't add that here, but that should be here. Okay, it's documentation. Proper documentation. Okay, when installing motor. Proper documentation. Alright, to take the data of the motor and what you are doing and the what comes out of it. Okay. Alright, now the operation starting. Okay, high current managed by starter. We made mention of the starter type. See that at starting, that's high current. That's what inrush. Okay, inrush current. You have to manage that by what starter. Okay, managed by starter. So high current. Then that's for starting. Then for running, the motor converts electric energy to mechanical energy. Okay, that's for motor. Generator does the opposite, converts mechanical to electrical energy. But motor converts electrical energy to what? Mechanical energy. Then for protection, okay, it's running to protection. Monitor faults and trips if needed. This is done by the protection devices. Okay, protection devices. So while it's running, if there's any faults, you trip off. Okay, then there's stopping/isolation. Safe shutdown for servicing. So when you run the motor, you want to do something with it, or you are done with it for that time, done with what you need the motor to do, you shut it down. Okay, you stop it or isolation. Okay, safe shutdown. Alright. So that's be all for this. Okay. Now, in case it appears like we are kind of rushing things here, recall that this is also part of the class recap series. So all we're doing is just recap, then touching the past questions and things like that. Okay. Now. What's this? Earthing. Because we said something about earthing, so let's quickly touch that. So for earthing, yeah. So like I defined just now, earthing, process of connecting the exposed metal parts of electrical equipment or solutions to the ground or earth using a low resistance conductor. Okay. Now it's just like saying you have, let's say, let's say this is your refrigerator, okay, now, and you have live and neutral connected to it, okay. Maybe this is not the best way to do it, but you get the point. Now, the metallic part of this fridge is not supposed to be connected to the live or the wire, okay. So when you make contact with it, the metallic part of the fridge is not supposed to shock or anything, so you are safe. Right, but if due to wear and tear, maybe the insulating part of the wire is bad or something, and there's a contact with the live wire with the metallic part of the fridge, this will lead to the metallic part having and it begin to conduct electricity. Meaning, if you make contact with it, current will flow to your body. Okay, and if you are not properly insulated, meaning you are making contact with ground. Okay, you are not putting on footwear like thick ones, you are making contact with ground, current will flow from live to ground, motion, and you are there, you get shocked. Okay, but if we earth this guy, here's where earthing comes in. If we earth this metallic part, to connect the metallic parts, let me use a different color, we connect the metallic part of this guy to ground, we connect it to ground. Okay, if we do that to ground, if by any means the live part connects to make contact with the metallic part, now the current has two options: either to flow through this part to ground, or flow through this part or through your body to ground. So current can flow through your body to ground or flow through this part to ground. Notice that this part there is no resistance, it just moves like this to ground. The resistance here can just be the cable resistance, which is less compared to the resistance of the human body. So this going through this path to ground, there's a resistance, the human body. Going through this path to ground, almost no resistance. If you say resistance of the cable, there's also a cable here. So I think that cancels out. But the point is, current flows through the path of least resistance. Therefore, this path offers less resistance to ground. So the current, instead of flowing through your body, giving you a shock, it will flow through this path to ground. So you will not get shocked when you hit your appliance. Okay? So that's the concept there, that's the idea. Okay? Now, so the purpose of this is to prevent faults. So that in the event of faults, like I said, e.g. live wire touches the metal casing, the fault current has a safe path to ground, preventing electric shock and allowing protective device fuse MCBs to operate. Okay? So why do we get an installation? Like this example just clearly states a lot. Yeah. So that example just states a lot. Okay. So safety of human life, prevent electric shock. Yeah. Quick disconnection. So allows force current to flow, tripping protective devices and fuse breakers. Okay. Then protect equipment, voltage stabilization, avoid potential build up. Okay. So ensures touchable surfaces stay safe. Yeah, because you will touch your fridge, you will touch it on your own. So you will make contact with it. So for that to be safe, that contact to be safe, then you have to exactly. Okay. So how can we reduce earth resistance of soil? Now, what does that mean? Notice that current flows through the path of least resistance. We said that. Current flows through the path of least resistance. So if the resistance of this part is very high, then that can lead to the current flowing through your body. Okay? But the point is, how can we reduce the resistance? Reduce the resistance. Not just the resistance of like this part, but even the earth, like where you connect this thing to the ground, to reduce that resistance. So how can we reduce earth resistance of soil? Now drive earth rods deeper. Reach lower, wetter layers of the soil. Your earth rod, connect it then deeper. Then use multiple rods connected in parallel. Space properly. Okay. Then water the soil or install in moist area. Add salt and charcoal. I think this one is very, very, very common. Okay. Very common. And when you dig the hole to put in your earth rod, you add salt and charcoal. Okay. To improve ion mobility. So yeah, to take in more of the like reduce resistance. Okay, in other words. So use chemical earth rods. Then use wider or copper plated electrodes. Then ensure good compaction of soil around rods. No air gaps. Okay. No air gaps. Alright, so I think that's for that. Then what is earth fault loop impedance? Okay, now earth fault, let me just quickly draw this. You know, we have power coming from the power line to your home. Okay, supply to your home, and then your DB distribution board, switch gear, everything. Then to your appliance. Okay, to your appliance, and then so current flows. And then flows back to the neutral back. Okay, now these parts, what's the resistance to these parts? Of course, it's connected to ground. This neutral is connected to ground where we have the transformer. Okay, so even this neutral is the earth of the transformer. Okay, so what we are saying now is okay, yeah. So what is the earth fault loop resistance loop? So earth fault loop impedance, okay, impedance is the total resistance or impedance of the fault current path from the live conductor through the fault down to earth wire through the installation earth back to the supply transformer via neutral and earth return path. Now look at this example here. You know, when this happens, this current flowing through this metallic part to the earth, this is not supposed to happen. This is a fault. Current is supposed to flow from the live to the back to this neutral, back to the source. But now it's flowing through this guy to earth. So fault. Okay, that's a fault. So the false current. So the current that flows through this part to it's the false current, and it flows down to earth. And then what's that part? What is that part? So you see from the live conductor through the fault down to the earth. I'm seeing it now. Through the installation earth back to supply transformer. Okay, via the neutral and earth return part. And there's a formula for it. Okay, so the ZX, which is loop impedance, equals external resistance or external impedance plus R1 plus R2, which is live and neutral. Okay, live and neutral, live and neutral. Then this equals what? We can write it this way: external plus what? Let me just use the word internal. Okay, external to internal. This external resistance impedance is from the transformer to your TB, and this is from your TB to your load back to the transformer, live and neutral. Okay, so that's just the concept there. Alright, then why is it necessary to have low edge fault or fault low impedance, which is this thing we're talking about? Why is it necessary? And it's to ensure high fault current. High fault current flows during fault. Okay, during fault. Yeah, which is this. This fault current, if you're not making contact with it, the current will not flow through to you. If it's not connected to ground, the current will not flow through to ground. The fault will just be on this metal metal body, waiting for whoever that want to make touch with it to get the person shocked. But if there is this part, it will ensure that that fault current will flow through this and not just here waiting to shock someone. Okay, so ensure high fault current flows during fault. Then high fault current allows fast operation of fuse and MCB. So when this current flows from this part to ground, it's no longer flowing from this part to this part. So when it's flowing to ground, or maybe there's a short circuit, it will make the circuit breaker strip off. So and that's kind of protection. Okay, that's why it's a protective device. If you reduce the risk of electric shock, we said that, and minimize fire risks, of course. Yes, because when the current flows through this part, instead of I've repeated it again and again. So instead of being here, like leading to overheat leads to fire. Okay, so instead of all that, the current flows to X. Alright, then complies with the standards. Okay, complies with the standard. Alright. Okay, then I think I skipped something here, which is this. Okay, these two are kind of similar. Okay, this and this. You can see that they are similar. Soil moisture, soil temperature, which is chemical, salt and charcoal. Okay. Okay, the notes that this formula is just repeated here. Okay, it's actually this. So let's take this stuff out. It's the same thing. Okay, so just take that out. Perfect. So yeah, let's go to these other parts. Okay, I think we have some calculation here. Let us quickly attend to this. So this is also part of the participation. So a 220 volt single phase domestic per unit rated at 8.5 kilowatts with a socket incorporated is to be installed from a distribution board located 18 meters away. Select the suitable cable size. That's what we have to do. So what we need to do, one, select the suitable cable size. Good. And determine the fault current. That's like the things we have to do in this question. If the LP impedance is of the transformer is this, the condition of installation include ambient temperature 45 degrees. Use reliable fuse to reach standard 3036 standard. Okay. Alright. Now these are the data. So we just do data collection. We just take all the data. Okay. Now something like I said something some minutes ago that in this course there are a lot of tables with data. So since this is what we have to do, let's focus on the cable size for now. So for the cable size, selection, for us to know what is the cable size to use, having this voltage and this power, to know the correct cable size to use, we need to calculate the cable current carrying capacity. For a cable size of 10 mm, there is an amount of current it can carry. It has a current carrying capacity. For 16 mm, it has a current carrying capacity. So if we know the current carrying capacity, we can know the size of cable to make use of. Do you understand? So what you have to do right now is to calculate the cable current capacity using what we have. And so now let's say IN. Let this be the cable current carrying capacity, IN. And this should be greater or equal to the load current. That is the whole circuit is designed to carry this amount of current. Okay, the whole circuit is designed to carry this amount of what? Current, and it will be divided or reduced by the correction factor K1. Correction factor. What's the correction factor? That means due to temperature, different temperatures will affect the conductivity, it affects the wire and things like that, the cable. So we take that into consideration. So the correction factor for ambient temperature, we take that into consideration. That's K1. Then also correction factor K2, we take that into consideration, which is what? The correction factor for British standard for 3036 fuse. Okay, 3036. That's what we are doing in the equation now. Let's be sure. Yeah, 3036. So there is a correction factor for this kind of fuse. So we also take that into consideration. Okay, so the temperature and then the fuse. Okay, correction factor for temperature and fuse. This will now divide the current you are expected to have. Okay, based on that power and voltage given. So let's call this equation 1. So when we get this, when we plug in the values, we'll now get the current, cable current capacity. Then we'll now go to the table for current capacity, as a rated capacity for cable size. We'll now go to the table and check which cable size match this value. That's the cable size we are going to select. Okay, so that's equation 1. So for K1 and K2, you can also get that from the table. Okay, get that from the table. The British standard table for the correction factor for ambient temperature and then correction factor for British standard 3036 fuse. So you can get that from the table. Now in the table, K1 is what? K1 for 45 degrees. Very important. For 45 degrees, because that's what they are giving the equation. 45 degrees C, K1 equals 0.75. K2 equals 0.725. Okay, 0.725. Then for IB, which is the total current we are expecting, as the current we are expecting to have in this circuit. Okay, to have in this circuit. Now that's the design current. Now for that, we can use this formula saying P equals IV. Is that also? Then making I suggest formula that will give us what? P over V. And power in this equation is given as what? Power in this equation is given as 8.5 Gs, 8,500, and then voltage is 220. So this will now be 8,500 over 220. That will now give us IB as what? IB as calculate, or let's see, that will give us what? 38.6364 ampere. Okay, now so we have all we need to calculate this current, cable current carrying capacity. So we just plug in all these values. 1, 2, 3, plug in all these values. So IN equals, this will give us, let's say it's 38.6364 divided by 0.75 times 0.725, and that will give us as what? 71.35 ampere. Okay, now since we have this, we'll go to the table. Okay, from the standard table for cable size, go to that table. And if you check the table, okay, if you check the table, you see that 10 mm, 12 mm. So you can see that we have 10 mm, 16 mm, 25 mm. Okay, and this is 50 ampere. This is 63 ampere. Like I said, this course is filled with tables and tables and tables. So this value we got now is between where? This and this. It's greater than this, or it's less than this. So we can just make it of what? 16 mm. So therefore, cable size equals 16 mm. This one I'm going to make it of. Okay. So that's all. Okay, so the next thing I'm calculating for is false current. And what we say false current, now that is false current. That's something that flows through the part where it's not supposed to. Okay, that's the false current. And false currents are kind of usually high because they flow through the part where they are not supposed to, and usually they have less resistance in that path. So they are not flowing through any load. So they are usually high. So how do you calculate the false current in this case? Okay. To calculate the false current in this case, what you do? From the formula for current, okay, or from Ohm's law, V equals IR, that means I equals, let me do this, that means I, false current, equals what? V over R. But in this case, impedance. In this case, we are working with AC, so voltage over impedance. But this impedance, since we are talking about false current, this impedance will be the total impedance, total earth fault loop impedance. Okay, so S just means total earth fault loop impedance, and that's impedance for earth is for the external impedance, that is from the transformer to your distribution board, plus the resistance or impedance from your distribution board to the load and then back to Earth. So that will be, let me use two different, but it's actually just this. But usually what we see is R1, R2. That's what we see in different textbooks and things like that. R1 live, R2 neutral. But together this is the resistance from your distribution board to the load and then back to X. Okay. So from transformer to your TV to that's fault loop back to the X. Okay. So this is the formula for it. And in the equation we are given this. We are giving this in the equation. We are giving this. Let's check. I think we are giving that in the equation. Where are you? Yes, we are giving this guy. We are giving. But what we don't have is this part. Okay, so we are treating this guy as 1. So let's just call this ZI or RI. Okay, repeat that as 1. Now we have the length of the wire as 18. It's in the equation. We have the length of the wire as 18, and it's copper wire. Okay, so since the length of the wire is 18, we are treating this as 1. Okay, since the length of the wire is 18 meters, that means this guy will be what? Equals 2 times 18. 2 times 18. Because you have 2 now, back and forth. Okay? Neutral and light. So 18 meters times 2. So 2 times 18 meters. Multiply by what? The resistivity of copper. And that's what? 0.0015. That's for copper. 15. That's this guy for copper. Rho for copper. Okay? Okay? So you plug in this value into your equation here. So ZS will give you this 0.2 plus 0.2 plus everything there is 2 times 18 times 0.0015, and this will give you 0.2414 ohms. Okay, then you substitute this back into this equation here, okay, and that will give you IF equals 220 volts over 0.2414 ohms, and that will work. So our fourth point is 911.3.3505 ampere. Okay, yeah. So that's it. So I don't this solution. You've been able to calculate the force current and then calculate and determine the cable size to make it off. Okay, so I done with this. What else? Let's see. Okay, so I think this last question we have here. So for luminous flux, what's the meaning? Okay, so it's just the loop. Okay, so I think it's the last question we have here. Okay, not much solving here. So what is luminous flux or light? Now, luminous flux is the total amount of visible energy emitted by a source per unit of time. Okay, so then just if you have a light bulb, okay, light bulb. Now, how bright is this bulb? And you know, light, based on the fact that there is an electric bulb in your room or light source in your room, you can see things around. So luminous flux, this is just the total amount of visible energy. That's energy, but visible. Okay, so it's what the human eye can see. It describes how much useful light is being produced. Okay, so what the human eye can see. Okay, so this part of this question is just basically reading, and then no nothing complex here. Okay, so what is the unit of light? Lumen. Okay, the unit of light, or you can say the unit of luminous flux is the lumen, and the unit of illumination, that means illuminance, this is lux. So for the unit of light, you write lumen, which is Ln. Then for the unit of illumination is lux, Lx. Okay, then lighting designed for computer office. Okay, now this is the part we'll do some calculation. So we are given these values. That the size of the room is 9 meters by 9 meters by 3 meters. Okay, so this is length, breadth, and then height. Okay, so of course the room is 3 dimensions, obviously. So we are required Okay, so the required illuminance is 350 to 400 lux. Okay, which is illuminance, the brightness of the room. Okay, it should be 350 to 400. Now, we are asked to use the lumen method for design. So, in order to do that, there's a formula for it. Okay, so in order to do that, the first thing we should do is to calculate the area of the room. Okay, to calculate the area of the room. Now, calculating the area of the room, that'll be what? That'll be what? So we have, let me just calculate it in 2 dimensions, okay, and then see something here. Let's see in 2 dimensions. So to calculate that, that will be what? Area equals what? Length times breadth times height, right? In 2 dimensions. This will give us what? 81 meter square. Okay, so using the lumen formula, okay, using the lumen formula, because we have to use the lumen method for the design. Using the lumen formula, it's what? We have total lumen, or total lumen required is what? Okay, now the area, okay, we have calculated the area to be what? 81 meters square. This E is the level of illumination. It's the level of illumination, which is what we have given here. Okay, so the level of illumination multiplied by the area, this will give us the total required illuminance, but required lumen. But the thing is this, we have to consider some other things, okay, like the utilization factor. Okay, that means the color of the room, different things around, objects around, those things will also affect the brightness. Okay, I believe we get what I'm saying. So since those things will affect the brightness, those things will affect the brightness, like the color of objects around, shades, things like that. That is the utilization factor. So that will affect the lumen required. Other thing that will affect it is what? Is the maintenance factor. Okay? So maintenance factor like dust and yes, things like that. So just to take those things into consideration. So those things will affect the luminance. Will affect the lumen required. So this is all I want to make it of. Okay? Now, for I think I should take this part out for now enough. So with this we already have the illumination level, and we are giving 350 to 400. But the mid value for 350 to 400, that's what I'm going to make it of. The mid value. We already have area at 81. Now note that the utilization factor ranges from 0.5 to 0.7. Okay? So utilization factor ranges from where? 0.5 to 0. Then for the maintenance factor, it's usually 0.8. One will mean like perfect, let me say perfect maintenance or close to perfect maintenance. So maintenance factor, things like this, most times they are usually clean. Okay, so we just use 0.8. Okay, there may be other factors, but most times 0.8 is used. Like I said, in this course, most things are gotten from tables. Most things are fixed values. Okay, or like almost fixed values. So this guy here, since things range from 0.5 to 0.7, we use the mid value, which is 0.6. Okay, so this is what we use for this guy, and so this for this guy. And then for the illumination level, since it's from 350 to 400, we use the mid value, and that will be what? 375. So we've gotten all we need. Area of calculated that to be what? To be 81 meters square. Okay, that's right. So let's go with that. So that will give us, or plug in all the values. So let me just use something to represent that. Total what? Let me just say total required lumen. Let me do this. Total required lumen. That'll be what? 357 times 81 all over 0.0 what? 6 multiplied by 0.8. That will give us what? 63281.25 lumen. Ln. Okay? Lumen. Okay? Total lumen required. Now, since we've gotten that, to choose the suitable light light fitting use LED bulb. Now each for LED fittings, each producing 3,500 lumen. That's for a standard 36 watt LED panel. Now for in that case, since each one produces 3,200, how many 3,200 do we have in this amount of lumen? Okay, so that will now tell us how many fittings, how many bulb we'll need. So what we just will say, the total number of fittings, total number of fittings. So that'll be what? Let me say FT. This will be what? What's this value again? 363,281.25 divided by 3,200. And you may be wondering, where do we get 3,200 from? Again, tables, standard values. Okay, and this will now give us what? To give us 19.7754. Of course, you can't really say 19.7754 fittings. This should be a whole number because it's number of fittings, number of points, number of LED, number of bulb. So that will now mean we will take approximately, or let's just say we take approximately 20 bulbs or 20 fittings. 20 fittings. Number of fittings. Okay, 20 fittings. Yeah, these are final answer. Okay. Oof, man, I think we're done with that. This will be all for this. This is all for this question. I think we've covered everything we need to cover in this course. For now, let me say for now, okay? For now. Okay, so this will be all for this video. Like, share, subscribe, comment, and then I'll see you in the next video. Thanks a lot for watching and bye for now.